Hello everyone, my name is Jin-Young Choi from Riverside. I will be presenting profiling for tiered memory. This work is collaborated with Sergey Gologodrov from AMD Research. In this presentation, we will present challenges in tiered memory architecture, and we explain existing hardware monitors and its pros and cons. Then we propose hybrid profiling method combining multiple hardware monitors together. Recently, memory technologies have evolved to deliver high performance and exascale computing. DDR technology faces scaling limit because DRAM cells are becoming smaller and smaller, then it is hard to maintain the reliable charge in a cell. Therefore, locating more cells into limited area increases the cost. The HBM is a technology that DRAM dies are stacked over the logic die, and those dies are connected with wider interconnect channels. With such design, HBM serves higher bandwidth compared to the DRAM. Intel released Optane memory. This technology can be applied to either DIMM-based memory or SSD. If we install the Optane memory into DIMM slot, then we can use it as byte addressable memory. Optane memory serves higher capacity compared to DRAM. With emergence of new memory technologies such as HBM or Optane memory access became heterogeneous. In tiered memory architectures, let me call this TMA, different memories such as HBM, DRAM, and PMEM can be mapped into a single byte addressable memory space. However, depending on the data location, memory access latency can be different. In the figure, HBM has the lowest access latency and PMM has the highest. In terms of capacity, HBM has the lowest capacity and PMM has the highest. In order to reduce memory access latency, we want to migrate hot data into fast but small memory. And also we need to eviction policy for cold data in fast memory because of limited capacity. Therefore, profiling memory behavior is a critical part in TMA. For the next slide, I'm going to explain challenges of TMA. The first challenge is a lack of visibility of memory access in software side. All memory accesses in software are translated into machine instruction, such as load store instruction. Load store instruction will be executed in processor's pipeline stage. Then all memory behaviors such as cache TLB lookup, page table walk, or DRAM accesses are served by hardware. Therefore, there is no direct interface between software and memory access. One point that software can get information of memory access is page default. However, page defaults are not complete metric for memory access. The occurrence of page defaults are not prevalent compared to other memory events such as cache or TLB misses. In addition, handling page default causes significant software overhead. For this reason, we need to get help from hardware monitors. Hardware monitors collect hints of memory access such as cache or TLB misses, and software can get fetch those information from hardware. That means those information is visible to the software. The next challenge is diversity of hardware monitors. The left-hand side table shows existing hardware monitors. We can check access bit in a page table entry whether MMU visited the page table because of address translation. Performance counters are well-known registers that we can gauge the system's overall behavior. IBS and PBS are AMD and Intel specific features to collect the system information. Even though we can use different hardware monitors, there is a lack of study on understanding pros and cons for each method. And the last challenge is profiling metrics for applications. These hardware monitors can provide different information. In this situation, combining different information is a challenge because of diversity. For the rest of the talk, we explain existing hardware monitors in background section. Then we propose tiered memory profiler. In evaluation, we evaluate different hardware monitors and page placement policies, combining different hardware monitors together. Finally, we will conclude this talk. Okay, to understand different hardware monitors, let's look at the table. Page table contains address translation between virtual and physical address. An access bit, let me call A bit, is a flag bit to indicate the page table is accessed or not. This method is universal, then it has no vendor dependency. With an A bit, we can track tail misses because page table is touched by MMU. This method is coarse-grained because A bit only shows it has been accessed or not. Then we cannot count the number of how many times it has been accessed with an A bit. Because A bit is in page table, we can track virtual and physical address. Performance counters are registers that show systems overall behavior. Supported performance counters are varied depending on architecture. Performance counters can collect the occurrence of hardware events such as cache or tailbit misses. This will show the number of occurrences, but it does not provide target address of events. This method will be useful to determine whether the system is under significant memory access or not. IBS is an AMD-specific feature. It collects an instruction in CPU's pipeline stage. Collected samples show some information such as cache or tailbit misses or node bridge status. Because it is trace-based, it is finer-grained than A-bit profiling. IBS can collect virtual and physical address of load store instruction. PBS is an Intel-specific feature. It is similar to the performance counter, but it can collect target address. In previous slide, we went through different hardware monitors. Also, we investigated pros and cons of each method. We proposed tiered memory profiler. I will call this TMP. Look on the left-hand side figure. We provide API that user space processes can interact with TMP. TMP daemon can directly interact with TMP driver. As you can see, TMP kernel driver combines different hardware monitor drivers, such as A-bit, IBS, PBS, and performance counter. With such a design, API can provide comprehensible memory access information to the application. Let's look at more detail about our implementation. This represents how the A-bit driver works. In order to visit page table to look at A-bit, we need to choose process IDs. Therefore, TMP daemon gets process IDs from top command, then filters process IDs based on usage of CPU and memory. After choosing PIDs, TMP requests A-bit checking for selected PIDs to A-bit driver. In A-bit driver, the driver traverses all valid page table entries in process's virtual address. In HPTE, driver checks A-bit and reset for the next epoch. If a page is accessed, driver increments A-bit count in page descriptor. Page descriptor is a per-page data structure. IBS and PBS driver is responsible for managing hardware features, including MSR registers, interrupt handler, and sampling rate. In order to collect samples from IBS and PBS, IBS-PBS driver should be enabled. After the initialization, MSR registers will collect samples. Then an interrupt will be generated at every sampling period. An interrupt handler will be executed, then it will store samples into memory buffer. The driver increments IBS PBS count in page descriptor. If profiling is not needed, TMP can disable IBS and PBS features. Since performance counters cannot provide target address of events, the main purpose of this feature is to provide the number of events to the application. Performance counter module reads register value and reset for the next epoch. This information will eventually be given to TMP daemon. This slide shows our testbed and workload setup. Look at the left-hand side table. We use AMD processor for the evaluation. Therefore, we evaluated IBS and 8-bit profiling. Also, all drivers and user space tools are implemented in Linux OS. On the right-hand side, we summarized workload setup. We chose memory-intensive cloud and HPC applications. In order to stress main memory, we created multiple instances for each benchmark. With TMP, we can generate heat maps that are outputs of tracking memory access with hardware monitors. Now we see two different heat maps of data analytics. On the left-hand side, it shows the result from IBS profiling, and on the right-hand side, it shows the result from 8-bit profiling. For each heat map, x-axis indicates the time in seconds. That means every second, the memory access is counted for each page. In y-axis, it indicates the physical address of pages. The reason why we chose physical address rather than using virtual address for representation is we want to represent memory behavior in multiprocess environment. Since physical address has the unique location in the memory, we can represent multiprocess memory behavior in same heat map. Finally, the color bar indicates the density of memory access per page. If the color is thicker, that memory region has more memory access. The first observation from heat map is we can see the hot region. This information can be used to decide memory allocation and migration policies. Next, we can see green circles. They show two different heat maps are not identical. That means each profiling method can collect different pages. This is the second observation that IBS and 8-bit can be complementary method to provide comprehensible memory access. This table shows the count of pages captured with 8-bit and IBS. In this experiment, we enabled both 8-bit and IBS simultaneously. In each column of detected pages, 8-bit means those pages are solely collected from 8-bit. IBS means those pages are solely collected from IBS. Then both means those pages are collected from both methods. The interesting part is pages collected from both methods are not many. That means 8-bit and IBS do not have big overlapping. Moreover, we can see the ratio of collected pages from 8-bit and IBS. The ratio is different in each benchmark. That means in some benchmarks, such as web serving, TLB misses are dominant. On the other hand, in data analytics, GOPS, and access bench, cache misses are dominant. This is another indication that 8-bit and IBS can be used together. To prove the validity of using 8-bit and IBS together, we performed trace-based simulation. In this experiment, we evaluate two different page placement policies. Oracle is a policy that application has knowledge on pages of how many times it will be accessed in the coming epoch. This represents the upper limit for policy design. History is a simple policy that brings epoch's hottest pages into Tier 1 memory. Now we show you the results of the trace-based simulation. This experiment assumes TMA has two tier memories, including Tier 1 and Tier 2. First benchmark, it shows the result of Oracle and history policies. Look at the graph. X-axis indicates the different profiling sources, and combined means it enables both ABIT and IBS. Y-axis indicates hit rates in Tier 1 memory, and epoch is equal to 1. That means every second we perform migration policy. And ratio indicates the ratio between Tier 1 and Tier 2 memory. First, in Oracle, combined profiling is always outperforming or matching others. However, in history policy, combined profiling is not always outperforming. At least it performs pretty well in most cases, because history policy cannot predict complicated memory access. For the rest of the applications, it shows the same observation that in Oracle, combined profiling is always outperforming or matching others, but in history, combined profiling is not always outperforming. Let me conclude my talk. Tiered memory architectures require careful resource allocation to maximize their efficiencies. In our best knowledge, none of existing profiling mechanisms can provide a complete picture of memory behavior. TMP provides comprehensible memory access information by combining multiple hardware monitors together. Finally, we can leverage TMP memory access information to achieve up to 70% better performance. Thanks for listening to my talk. If you want to see more detail about this work, please read our full paper or visit our website. Thank you so much.